the end. So let's take a look at greenhouse gas reduction of RNG. First off, to be clear, renewable natural gas is produced from waste, not from crops. So it's not a food crop that could be used to supply product or feed families, to feed nations. It is truly waste product that either could come from livestock, could come from crop waste, could be in a landfill. And through anaerobic digestion and further processing, it's converted, meaning the methane is captured from escaping into the atmosphere, where, by the way, it's 30 times more potent than CO2. Although it lasts for a shorter period in the atmosphere, it's 30 times more potent than CO2. So taking a look at that, when we get a lot of questions around renewable natural gas, well, do you have renewable natural gas systems? Do you have, compressed natural gas systems? It's the same. It's the methane molecule. It's just a different source, whether it's geologic natural gas or crop-based natural gas. There's no difference in the systems. So looking at the greenhouse gas reduction and taking a look at what that means, up on the top of this graph, you will see RNG. You'll see natural gas in the bluish, the geologic natural gas, which is about a 15 to 18% improvement over that red line, which is diesel, the baseline. So 663 grams per kilometer is emitted from a fossil diesel or geologic diesel. When you look at geologic natural gas, you get about an 18% improvement right away. When you start looking at RNG, especially RNG that comes from manure, it's a 200% improvement over diesel. And even RNG from crop waste, wastewater, landfill is still at least an 80% improvement over diesel. The exciting thing is when you look at it compared to the EU grid in 2019, nothing has the negative sink that RNG from manure has. And even brown electricity and coal, you can see it's extremely dirty. Hydrogen from natural gas is about the same as geologic natural gas, and even green hydrogen and wind power has some sort of emission in the creation of the equipment to create that. So if we were to look at all the available sources of energy to be supplied to the heavy duty sector, the cleanest by far today is renewable natural gas. So we tick the box and say, yes, it's very clean. Now we have to say, okay, but is there enough? Is there enough available to really make an impact? So to do that, we have to define how much energy is required for the heavy-duty transport sector. And we're going to use a term called exajoule, which is basically 1,018 joules of energy required. And if we look at the North American marketplace, and specifically the targeted sector that we're looking at is the heavy-duty transport sector, North America requires approximately 5 exajoule, or EJ, of energy per year to meet that demand. So that's the basis and the scope of what we're going to talk about when it comes to biomass supply and RNG. Taking a look, the study determined that if you look globally, there's about 30 exajoules of demand in the heavy-duty transport sector globally, North America, Europe, and rest of the world. But there's about 31 exajoules of biomass, meaning waste product that's out there. And WHO is in EPA in North America stating that they expect a 59% growth in waste creation between now and 2050. So we've got a waste problem and we've got an emissions problem. It makes perfect sense to use the waste to reduce the emission problem. When we look at North America, we see the demand for the heavy-duty transport sector to be 5 exajoule. But as the study calculated, there's about 7 exajoule of biomass available. When we look at that further and break that down of where it's coming from, today North America produces less than 1 exajoule of renewable natural gas. So it's virtually an untapped market, 70x growth of the total 7. Wastewater is a little less than 1 exajoule. Landfill waste is about 1.3. These numbers are rounded. Manure is about 1.9. And then agricultural waste is 4, making that 7. When we look at that more specifically, we're being realistic here and saying, some of this is very hard to get to. So this graph shows of the 31 exajoule that's available globally, about 17% is relatively easy to get at, and that would be wastewater and landfill biomass that is probably near pipeline or close to pipeline. It's easily processed and easily accessed. So that's the 17% that we have circled here to say, if we can access that, could we feed the heavy-duty transport sector in the various markets such as the EU and North America? And the determination of the study is, yes, we can, and we can support that market, and we'll give you some of the numbers on that. So we've determined that there's enough biomass potentially available with significant growth possibilities into the future to support RNG supporting the heavy-duty transport sector. Now let's take a look at technology. What sort of technology is required to do that? Today, as we said, we're agnostic when we look at our solutions. So BEV today, and what we're trying to do is be realistic in upfront capital costs of a vehicle and not degrade the performance, meaning you're going to put 10, 15, 20 battery packs onto this vehicle, and yes, you can get range, but the cost of it's prohibitive. Today's electric Class 8 truck, 200 to 250 mile range with realistic battery packs. In hydrogen, you can go 400 to 500 miles. You start getting into some cost on the system on those. Today's natural gas solutions, the back of cab solutions we have are about 850 miles range. And then we spoke about sleepers. All of this depends on payload too. If you're hauling potato chips, it's a lot different than if you're hauling steel, and there's differences. Yes, we can easily get 500 miles in a BEV solution, but it's going to require a 1,000 kilowatt battery pack. And on hydrogen, we can absolutely pack more hydrogen on there, but you're going to be taking up more space and you're going to be having more capital upfront costs. Not to mention in both cases that the North American marketplace is not ready to support an electrical grid that would require one Class 8 truck having the same electrical consumption in a day as 29 to 30 homes. And on hydrogen, the infrastructure for hydrogen filling is still a long way off on development. The study concluded that if we were to look at natural gas or look at BEV, hydrogen, where does it make most sense now through 2030 and even beyond for the particular energy sources to solve? And we believe there's not one solution, there's multiple solutions, and we should access those in parallel. So you can see here the study determined that in city hall applications, BEV makes a lot of sense. We know that we can achieve 200, 250 mile range. In LCV, your energy requirements are a lot less than when you look at heavy-duty truck down on the bottom, where you could have a 80,000 GVW and need 500 to 800 miles a day in range if it's a sleeper application. So the study determined that for compressed natural gas, the real sweet spot is down in the lower right. That high payload, long-haul application. And by the way, in that application in North America, there's 200 to 250,000 heavy-duty trucks per year that go into that marketplace. So that's really the target market and the sweet spot for a renewable natural gas solution. So, is it available? If I'm a fleet and I want to access it, do I have an issue that it's not available? Today, as we stand, looking at across the multi-mode different platforms that there are, heavy-duty truck, refuse, bus and coach, and medium duty, in North America, there's over 100 OEM available platforms in compressed natural gas solutions by the various OEMs that you see at the bottom, Volvo, Mack, Kenworth, Freightliner, and the transit OEMs, as well as Europe. And we'll talk to you about OEMs releasing more platforms to cover more of the applications in this space. So we tick the box, technology's in place, supply potential's there, it has excellent greenhouse gas reductions. Now I'm going to ask Ashley Remillard to come up and tell us what's going on with the regulatory